Welcome, dynamics students. This mini lecture is on the topic of rigid body kinetics, not kinematics, kinetics. So now we're going to look at what happens when we apply forces and moments and track a body's resultant motion. In previous lectures, we've dealt just with with kinematics of rigid bodies undergoing planar motion. And we've looked at how they've moved and how the fact that a body is rigid and therefore the distances between all of its points have to stay the same, and the constraints of planar motion, where all of those points are moving exclusively in a single plane and the vector of all moments is basically the normal to that plane, how all that adds up to allow us to describe motion of a rigid body, including both translation and rotation. Now we're going to look at what caused that. And we're going to take a bit of a step back before we dive into free body diagrams and then resultant accelerations, both rotational and translational. And we're going to look at a very important quantity, basically a characteristic of any kind of rigid body, and that is the mass moment of inertia. A general rule of thumb that you can think about in terms of the kinetics of rigid bodies, or really the kinetics of any body, is that we can look at mass, in kilograms or slugs or whatever, as being the quantity upon which acceleration operates, so to speak, to give a force, or if working at a distance, to give a moment. But we look at moment of inertia as being sort of the quote-unquote mass quantity associated with a body that's undergoing rotation. So if we apply a moment, we will get an angular acceleration, that's our Greek letter alpha, depending on the mass moment of inertia of that body. So just generally speaking, let's get a pen here. If we apply a moment, so we'll call it the resultant moment, to a rigid body, we will end up with an angular acceleration depending on the moment of inertia of that body. So that's our general rule of thumb. Now, from the standpoint of planar motion of our rigid bodies, what we really care about is the what's known as the polar moment of inertia. So that's the moment of inertia that's required to make a body spin around an axis that's pointing normal to the surface that the body can move in, because that's the only direction those rigid bodies can rotate. So we'll be practicing with that a little bit, but we're going to start with a very, very basic problem where we just reinforce our understanding of the definition of moment of inertia. And we're just going to do a quick integral in this problem. So here's our coordinate axes, and we've got a rod, and it's slender, but not too slender. We can assume it has an area. Here, A. It's got a length L. And we're asked for the problem, what is the mass moment of inertia of that rod about the y-axis? Rod. So to get that, we need to think about the definition of moment of inertia of anything. And the general definition, I about some axis, in this case y, is going to be the integral over the whole mass of the distance of any point on, any mass bit on that body squared from the y-axis. We'll say r to the y-axis dm. So what we're doing is we're adding up over the whole mass of the body the square of the distance of that mass bit from the axis that we care about. So in this case, we care about the y-axis. What we'll end up looking at for rigid body planar motion is we'll end up adding up the distance of those mass bits of any body from the planar normal to the planar that we're undergoing motion in. So that's something we'll see But this rod could be moving in, say, the ZX plane and maybe rotating around the y-axis like a pinwheel maybe, so we'd be concerned with that kind of rotation. We might want to know that. So we're going to be looking at the rod basically rotating about a point here at the origin, such that the axis of rotation is the y-axis. So this is very different than rotating about its center point or its center of mass. So we can use this fundamental definition to calculate I sub y directly, or we can look up maybe a formula in the back of our book or in a handbook for what would be I, in this case IY or IZ, at the center of mass of the rod, and then add R from the center of mass to the y-axis connection point times the mass. So we could use the parallel axis theorem as well. But for this exercise, we're just gonna integrate simply and refresh ourselves about how to use, just the basic definition of a bit of mass being at a given radius from the axis about which we're rotating, squared, and then integrating over the mass bit. So we're told in this case that we have a uniform density. So what that means from our standpoint is we can pull density out of our expression and we can end up with I sub y equaling a function of volume. So we'll go from the radius squared from any point to the y-axis. We're going to integrate over the whole volume. So as was the case with things like centroid and center of mass, next our objective is to identify a volume element, dV. So we can take a look at this rod. Let's blow it up here a little bit. This is a pretty simple problem, but we're just making sure we understand this. So if we look at length of dx along this rod, we can define a volume element equaling the cross-sectional area A times a length element, a little bit of length. Well, the length is in the direction x, so dv we could say it's a times dl, d length, a little length element, but length is in the x direction, so our dl is dx. So, and a is constant with x. A is a constant. So we can say that our volume element dv is a dx. So we can put that back into the integral. And we can also say, another important thing is we can say, where is that volume element? So let's draw that in red. Let's just define any little volume element here. There's a volume element. Well, how far is it from the y-axis? Well, it's length x from the y-axis. So we can define the radius from any point of any bit of mass to the axis about which we are going to rotate. In this case, is just x. So I can define I sub y equals a times the density times the integral of x squared dx. And we're going to integrate, in this case, from x equals 0 to the full length of the rod. So there's my limits of integration. So that's going to give me a times the cross-sectional area times the density times 1/3 x to the third integrated from 0 to L. So I sub y just equals our density times the cross-sectional area times L times L squared over 3. So that's popping in those limits of integration and rearranging a bit. So I had 1/3 L cubed times A times rho, the density, but I took one of those L's out and I combined it over with the rho and the A because that allows me to express this as the full mass of the rod. Density times the area times the full length gives me density times volume, so that's mass. So I can say the mass moment of inertia of the rod about the y-axis is the rod's mass times its length squared divided by 3. And that is basically the moment of the mass moment of inertia of any rod about its endpoint, and that's something very, very useful for solving a lot of kinetics problems. So that concludes this mini lecture. This was just a quick review of the definition of mass moment of inertia. Important points: definition, identify the axis that we care about, what we're rotating about, identify a bit of mass, a mass element that's associated with the body, figure out a weight, a function that describes the radius of that mass element from the axis that you're rotating around, pop it into our formula, basically square it, and then integrate with respect to the mass element. If we have uniform density, we can pull density out and we can just integrate over the full volume with respect to a volume element. If density varies with location, then we would just have a function within the integral that we would integrate along with the rest of the volume. No problem, just a little bit more complicated integrand. And then it's quite often very, very useful to describe the moment of inertia in terms of the mass of the body itself, and then some length unit that we're going to end up typically expressing in terms of some dimension of the body itself. And last but not least, remember that mass moment of inertia will always be in mass times length squared. So if you get a different set of units, check your integration and make sure you didn't make an error. So we will have one more practice after this where we'll look at the parallel axis theorem, and we'll look at combining mass moments of inertia, a composite addition, and then we'll go ahead and use that in problems where we apply kinetics and looking at summing moments and finding the rotational acceleration of rigid bodies.